The stars above hold a secret humanity has chased for centuries. We are closer than ever to discovering if we share this cosmos with other living worlds. This journey takes us beyond science fiction to the cutting edge of discovery, where astronomers have pinpointed 30 planets with the potential to host life. By the end of this exploration, you will know the most promising addresses for life in our galactic neighborhood. We will uncover worlds bathed in eternal red light and oceans that might swirl under thick alien skies. What does it feel like to stand on the brink of such a profound discovery? Our cosmic backyard holds a world that could rewrite our place in the universe. A mere 4.24 light-years away, a planet named Proxima Centauri b orbits its faint red sun. This is not a distant point of light in a telescope. It is our next-door neighbor, a rocky world with a mass strikingly similar to Earth, nestled within its star's habitable zone. This is the region where temperatures are just right for liquid water to potentially exist on the surface. Imagine vast, dark oceans shimmering under a deep crimson sky. But this alien paradise comes with extreme conditions. Proxima Centauri is a red dwarf, a star known for its violent temper. It frequently erupts with powerful stellar flares, bombarding the planet with radiation that could strip away any atmosphere and scouring the surface of life as we know it. Another fundamental challenge is tidal locking. The planet is so close to its dim star that one side is perpetually bathed in daylight, while the other is frozen in eternal night. This could create a world of dramatic extremes, a so-called eyeball Earth. A single, stable ocean might pool under the direct stare of the star, surrounded by a ring of ice that gradually gives way to a global glacier on the dark side. Could life find a way in that thin, temperate border between fire and ice? The answer may be waiting right on our cosmic doorstep. Yet the search for life does not end at our nearest stellar neighbor. Venture just under 40 light-years away, and you will find a solar system that defies imagination. Orbiting an ultra-cool dwarf star named TRAPPIST1 is a family of 7 rocky worlds, each remarkably close in size to our own Earth. This compact system is a cosmic archipelago, and at its heart lies a world of profound interest, TRAPPIST1e. This planet sits perfectly within its star's habitable zone, that cherished orbital region where temperatures could allow for liquid water to flow. But this is not a sun like our own. The star is a dim, Jupiter-sized ember, bathing its planets in a perpetual, gentle twilight. If you were to stand on the surface of TRAPPIST1e, you would see not one, but several of your sibling worlds hanging in the sky, some appearing larger than our own moon. The potential for water here is staggering. Scientists believe this world could be entirely shrouded by a single, globe-spanning ocean, a water world with no land in sight. The key to unlocking this mystery lies in its atmosphere. Does it possess a thick, protective blanket of gases that could regulate its climate and shield it from stellar radiation? This is the very question the James Webb Space Telescope is designed to answer. By analyzing the starlight that filters through the planet's atmosphere, we can search for the chemical fingerprints of water vapor, methane, and even oxygen, gases that could hint at a living world. Is this serene, water-drenched planet our best hope for finding another home for life in the cosmos? 500 light-years from Earth, in the constellation of Cygnus, another milestone in our search awaits. This is Kepler 186f, a world that forever changed our perspective. It was the first planet we ever discovered that was nearly the size of our own Earth, and it was found orbiting comfortably within its star's habitable zone. Before this moment, we could only wonder if other Earth-sized worlds existed in that cosmic sweet spot. Kepler 186f proved they do. This distant, rocky world circles a star much cooler and redder than our Sun. Standing on its surface would feel like being in a perpetual, deep sunset. The entire landscape would be bathed in a dim, crimson light, a stark contrast to our bright blue and white skies. For any plant life that might evolve here, this presents a fascinating challenge. On Earth, plants use the full spectrum of our yellow sun's light for photosynthesis. But under the faint red glow of this star, any potential flora would need to adapt in extraordinary ways. Perhaps leaves would be black or deep purple to absorb every possible photon of the limited red light available. The very nature of life's energy cycle would be fundamentally different from our own. This world is a testament to the diversity of habitable real estate in our galaxy. It showed us that Earth twins are not just science fiction, but tangible targets in our quest. What kind of life could thrive in an endless ruby twilight? Far from the dim red suns we have explored lies a world orbiting a star strikingly familiar to our own. Kepler 452b circles a G-type star, a virtual twin of our Sun, but one that is 1.5 billion years older. This planet, often called Earth's cousin, offers a vision of a world that has experienced a stability we can only imagine. It has spent 6 billion years within its star's habitable zone, a calm, life-friendly orbit that has persisted for far longer than Earth has even existed. Think about the sheer span of time this represents. While life on Earth was just single-celled organisms, this world could have been enjoying conditions ripe for biology for billions of years. What kind of evolutionary journey could have unfolded in that vast additional head start? The planet itself is a super-Earth about 60% larger than our home. This greater size brings with it a profound physical reality, a stronger gravitational pull. Walking on its surface would feel like carrying a heavy backpack at all times. This intense gravity would sculpt a world unlike our own. Mountains could not soar as high as our Himalayas, constantly pressed down by the planet's greater weight. The atmosphere would likely be thicker and denser, potentially creating a powerful greenhouse effect that traps heat. Yet this very same gravity could be the key to its long-term survival, holding onto a protective atmosphere far more effectively than Mars ever could, shielding any potential life from the harshness of space. Could this older, larger, and stronger version of Earth be a glimpse into our own planet's distant future? Or is it a completely separate chapter in the story of life in the cosmos? Another world of immense promise lies a mere 40 light-years away, orbiting a quiet red dwarf star. LHS 1140b is a super-Earth, a dense, rocky world that has astronomers particularly excited. Its true significance lies not just in its location within the habitable zone, but in what we have learned about its composition. Careful measurements reveal this planet is incredibly dense, far denser than our own Earth. This points to a world with a massive, iron-rich core and a robust rocky mantle, a structure that suggests it is a true terrestrial planet, not a gaseous mini-Neptune. That dense, solid foundation is crucial, but it is the potential for an atmosphere that makes this world a top candidate for life. A planet with such strong gravity is perfectly equipped to hold onto a thick atmosphere, a protective blanket that could be its greatest defense. The red dwarf star it orbits is relatively calm for its type, but it still emits harmful radiation. A substantial atmosphere would act as a shield, deflecting and absorbing these dangerous particles, while also distributing heat around the planet to create a more stable, temperate climate. This combination of a confirmed rocky world with the likely presence of a life-sustaining atmosphere makes LHS 1140b one of the most compelling targets for the next generation of telescopes. We are not just looking at a dot of light anymore, we are looking at a world with all the right ingredients. The question is no longer if it has the potential, but what we might find when we finally peer into its skies. Just 11 light-years from our solar system, a world of quiet promise orbits in the cosmic dark. Ross 128b is an exoplanet with a mass strikingly similar to Earth, and it resides comfortably within its star's habitable zone. But its true distinction lies not in its position, but in the character of its sun. Unlike the violent tantrums of Proxima Centauri, the red dwarf star Ross 128 is remarkably calm. It exhibits very low flare activity, offering its planetary companion a rare gift in the red dwarf family, a stable and far less hostile environment. This stellar tranquility dramatically increases the chances that Ross 128b has held onto a protective atmosphere, shielding its surface from the eroding power of cosmic radiation. Imagine a world where the primary threat to life has been dialed down, a place where the star in the sky is a steady, gentle ember rather than an unpredictable flare gun. This stability opens the door for complex chemistry to proceed uninterrupted, for oceans to persist, and for any potential life to evolve without the constant threat of stellar sterilization. In the search for a habitable world, a quiet star might be the most valuable neighbor of all. Could this peaceful planet, so close to us, be the serene oasis we have been searching for? 31 light-years from Earth, a world named GJ357d holds a secret beneath its potential blanket of clouds. Discovered by NASA's TESS satellite, this super-Earth is a heavyweight, possessing at least 6 times the mass of our own planet. That immense bulk places it squarely within its small, cool star's habitable zone, a region where temperatures could allow for liquid water to exist. But the nature of this world is a subject of intense speculation. With such a significant mass, it could be a dense, rocky titan, a planet with a solid surface and a powerful gravitational pull. Yet another, even more captivating possibility exists. GJ357d might not be a rocky world at all, but a vast, globe-spanning ocean. Imagine a planet with no continents, no mountains breaking the surface, just an endless, deep ocean that circles the entire world. The pressure at the bottom of such a sea would be unimaginable, creating layers of exotic ice that behave more like hot rock than frozen water. In the eternal twilight of its red sun, this water world could host environments in its dark depths that are completely isolated from the stellar energy above, relying instead on hydrothermal vents or chemical soups for sustenance. Is this distant super-Earth a rugged, oversized version of our own? Or is it a profound aquatic abyss, a completely different chapter in the story of what a living world can be? The quietest stars often hold the deepest secrets. Just 12 light-years from Earth, a dim red dwarf named Tegodon's star hosts a planetary system that captivates astronomers. Orbiting this ancient, ultra-cool ember is a world called Tegodon's star B, a planet with a mass almost identical to our own Earth. It sits squarely within its star's conservative habitable zone, a region where a planet could maintain liquid water on its surface with even a modest atmosphere. The temperature here might be remarkably Earth-like, a gentle balance between the cold of space and the faint warmth of its small sun. But the most profound aspect of this system is not its current state, but its incredible age. Tegodon's star and its planets are likely billions of years older than our entire solar system. Contemplate the sheer weight of that extra time. While our sun was still a fiery infant, this distant world may have already been a stable, rocky planet with oceans and continents. Life on Earth took nearly 4 billion years to evolve from single-celled organisms to complex animals. Imagine the evolutionary pathways that could have unfolded over an additional 3 or 4 billion years on a world like Tegodon's star B. What forms of life could have arisen, adapted, and perhaps even achieved intelligence in that vast, silent expanse of time? This is not just a planet that might be habitable today. It is a world that has had an almost unimaginable head start. But the story of this ancient star does not end with its promising inner world. Tegodon's star C, the system's second known planet, presents a starkly different vision of habitability. Orbiting on the cold, outer fringe of the habitable zone, this world receives far less warmth from its faint sun. Its surface temperatures are likely frigid, potentially locking the entire planet into a global ice age, a perpetual snowball state. Imagine a landscape of endless white where glaciers stretch to the horizon under a dim, red sky. Yet even here, life might find a foothold. A thick atmosphere rich in greenhouse gases like carbon dioxide could act as a planetary blanket, trapping enough of the star's feeble heat to create regions of liquid water. Alternatively, the planet's own internal furnace could provide the key. If Teegarden's star C is geologically active with a hot core like Earth's, volcanic vents on the ocean floor could melt through the ice, creating vast subsurface lakes. These hidden aquatic oases, warmed from below and shielded from the frozen surface above, would be completely isolated from the star's light. Entire ecosystems could thrive in these dark, warm waters, powered not by photosynthesis but by chemical energy from the planet's own heart. This offers a completely different blueprint for life, one that does not rely on a friendly star but on the enduring heat of a world itself. Is the most resilient life in the universe not in the temperate zones but hidden deep within the ice? Sometimes the most profound discoveries begin with a single molecule. 120 light-years away, in the constellation of Leo, the planet K218b revealed a tantalizing clue in the search for life. Scientists detected the clear signature of water vapor in its atmosphere. This was not just another exoplanet, it was a world that had answered one of our most fundamental questions with a resounding yes: water is out there. This super-Earth orbits within the habitable zone of a quiet red dwarf star, a region where temperatures could allow that water to exist as a liquid. But what kind of world is K218b? Its size places it in a mysterious category, larger than our own rocky Earth but smaller than the ice giant Neptune. This middle ground is the heart of a fierce scientific debate. Is this planet a massive, rocky world with a thick, extended atmosphere, a place where vast oceans could swirl under a dense, cloudy sky? Or is it something entirely different, a so-called mini-Neptune? A mini-Neptune would have no solid surface for an ocean to rest upon. Instead, it would be a world with a relatively small rocky core, smothered under a deep, crushing envelope of hydrogen and helium gas. Descending into its atmosphere, you would encounter ever-increasing pressures and temperatures, the gases slowly turning into a hot, dense fluid until any notion of a shoreline is lost forever. The presence of water vapor is thrilling, but its meaning depends entirely on which of these two worlds K218b truly is. Is it a water-rich super-Earth, a potential haven for life, or is it a gaseous world where the water exists only as vapor in an uninhabitable, crushing sky? The answer will redefine our understanding of where life can truly begin. The ambiguity of worlds like K218b pushes our search toward targets with fewer mysteries. Among the most promising is a planet known as TOI 700d. Discovered by NASA, a TESS satellite, this world is a near twin to our own in size, a rocky body almost exactly as large as Earth. It orbits within the habitable zone of a quiet M-dwarf star, a star that shows little of the violent flare activity common to its kind. This stellar calm is its first gift, a stable environment where an atmosphere could persist over billions of years. The planet completes one full orbit around its dim sun every 37 days, a rapid year that places it close to the star, but within that precious temperate belt where water could flow. This proximity, however, comes with a likely consequence. TOI 700d is almost certainly tidally locked to its star. One hemisphere is locked in permanent daylight, while the other is trapped in an endless frozen night. You might think this creates a simple world of scorching heat and absolute cold, but climate models reveal a far more nuanced and hopeful picture. A thick, Earth-like atmosphere could work wonders here. Powerful winds would constantly circulate between the hot and cold sides, redistributing heat across the entire globe. This could create a vast, temperate twilight zone along the terminator line, the border between day and night. Within this band, conditions might be just right for lakes, rivers, and even vast oceans of liquid water to exist. Some simulations even suggest the entire dayside could be covered by a massive, reflective cloud deck, acting like a planetary sunshade to keep surface temperatures mild. This is not a world of simple extremes, but one where dynamic weather and a robust atmosphere could forge a surprisingly habitable environment. With its Earth-like size, quiet star, and strong potential for surface water, TOI 700d stands as one of the highest priority worlds for our next great observatories. We are not just looking for planets in the right place, we are looking for worlds that have all the right tools to build a stable home. A triple star system paints the sky of a distant world. GJ667cc is a super-Earth that does not orbit a single star, but exists within a complex family of 3 suns. Its primary star is a dim red dwarf, and this planet circles tightly within that star's habitable zone. Imagine the view from its surface. Not one, but 2 other stars would hang in the heavens, appearing as intensely bright points of light, casting multiple, shifting shadows across the landscape. One would shine with the brilliance of our full moon, the other almost as bright. Days would be a complex dance of light, with sunrises and sunsets involving multiple celestial bodies. This world scores remarkably high on the Earth Similarity Index, a measure that compares its properties directly to our own planet. It has a similar mass and receives a comparable amount of stellar energy, suggesting it could be a rocky world with a temperate climate. Yet the very nature of its stellar neighborhood complicates this promising picture. The gravitational tug of 3 stars creates a dynamic and potentially unstable environment. A planet's orbit can be perturbed over long timescales, pulling it in and out of the habitable zone. Furthermore, the light from multiple stars makes it incredibly difficult for our telescopes to peer into this world's atmosphere. The stellar signals are mixed and muddled, obscuring the subtle chemical fingerprints we desperately seek. Is GJ667cc a true Earth analog blessed with multiple suns, or is it a world caught in a gravitational ballet too chaotic for life to take hold? The answer is hidden within the tangled light of its 3 parent stars. 44 light-years away, a world spins freely in its orbit, offering a rhythm of life we would instantly recognize. This is HD 40307G, a super-Earth that breaks the mold of the tidally locked worlds we so often find around dim red dwarfs. It orbits a K-type star, a star that is slightly cooler and more orange than our own Sun, but significantly larger and brighter than the faint red embers we have encountered. This star's gentle nature grants HD 40307G a much wider orbit within the habitable zone. A single year on this planet lasts about 200 Earth days, a longer, more leisurely journey around its sun. But the true gift of this wider orbit is rotation. The planet is far enough from its star's gravitational grip that it is not forced to show only one face, a condition known as tidal locking. Instead, HD 40307G likely spins on its axis, creating a familiar cycle of day and night. Imagine a world where the sun rises and sets in an orange sky, where temperatures have a chance to moderate between the warmth of day and the cool of night. This daily rhythm is fundamental to life on Earth, driving weather patterns, photosynthesis, and the very biological clocks of countless organisms. A world with a true day-night cycle presents an environment where life as we understand it would not have to solve the puzzle of eternal daylight or endless darkness. It could simply adapt to the rising and the setting of the sun, just as it has here for billions of years. Could this spinning super-Earth with its familiar celestial rhythms be one of the most Earth-like environments we have yet discovered? The search for a second Earth leads us 1,200 light-years away to a star slightly cooler and older than our own. Kepler 62f is the outermost of 5 known worlds in this distant system, a planet almost exactly the same size as our home. This Earth-sized traveler orbits a K-type star, bathing in a gentle orange light. Its position in the habitable zone is more distant and leisurely than our own, taking 267 days to complete a single year. This greater distance from its parent star presents a fundamental climatic challenge. The sunlight reaching Kepler-62f is significantly fainter and less energetic than the light that warms our planet. Without a powerful mechanism to trap that heat, this world would likely be a global ice ball, a frozen wasteland where all water is locked in permanent ice. The key to its potential habitability, therefore, lies in the composition of its air. For liquid water to flow on its surface, Kepler-62f would need a thick atmosphere rich in greenhouse gases like carbon dioxide or methane. This atmospheric blanket would act like the glass of a planetary greenhouse, allowing the star's faint light to enter but preventing the resulting heat from escaping back into space. Such an environment could maintain vast, cold oceans, perhaps shrouded under a perpetual, hazy sky. The very conditions that would make this world livable would also make it profoundly alien. Its landscapes would be shaped by a different kind of sun, and its potential biology would have to adapt to a colder, dimmer reality. Could this distant, Earth-sized world be a frozen globe waiting for a greenhouse to awaken it? Or is it already a hazy, temperate planet teeming with life beneath its insulating clouds? A world bathed in the gentle glow of an orange sun holds a unique distinction in our cosmic search. Kepler-442b orbits a K-type star, and it receives a flow of light from its sun almost identical to the amount of energy Earth gets from our own. This precise stellar illumination makes it a standout candidate for life as we know it. The planet scores remarkably high on the Earth Similarity Index, a scientific measure that compares an exoplanet's properties directly to our own world. With a radius only 1/3 larger than Earth's and a likely rocky composition, it feels reassuringly familiar, but its true advantage may lie in the nature of its star. K-type stars like this one offer a more stable and long-lasting environment than our own sun. They burn their fuel more slowly, granting them lifespans measured in tens of billions of years, far longer than the sun's 10 billion-year existence. This extended stability provides an almost unimaginable window for life to arise, evolve, and thrive. For any potential flora on Kepler-442b, the conditions for photosynthesis would be nearly perfect. Plants would not need to adapt to a dim red light or a perpetual twilight as on other worlds. They could harness the star's energy using pigments and processes very similar to those found in Earth's forests and fields. Some researchers argue this world could be even more hospitable than our own in one crucial aspect: its steady and reliable stellar energy flux. Our own sun can have periods of increased activity that disrupt atmospheres and climates, but this older, K-type star provides a constant, gentle warmth. This planetary cousin, with its familiar light and promising stability, forces us to reconsider what the ideal stellar neighborhood for life might be. Is the perfect Earth analog not a world around a sun-like star, but one basking in the enduring orange light of a quieter, more ancient sun? 14 light-years from Earth, a super-Earth named Wolf 1061c orbits a quiet red dwarf star. This world is one of our very closest neighbors that resides within the habitable zone, a tantalizingly short cosmic distance away, but its promising location comes with a critical caveat. The planet sits perilously close to the inner edge of its star's temperate belt, skirting the border of what could be a climatic furnace. This precarious position places Wolf 1061c at a dramatic crossroads. It could have experienced a runaway greenhouse effect, a catastrophic chain reaction where a planet's oceans boil away, filling the atmosphere with steam that traps even more heat, leading to a surface hot enough to melt lead. This is the fate that many scientists believe befell Venus, turning a world once potentially Earth-like into a scorching hellscape. If this is the case, Wolf 1061c would be a superheated twin of Venus, a stark warning of how easily a habitable world can be lost. Yet there is another, more hopeful possibility. The planet's significant mass, several times that of Earth, could have allowed it to hold onto a tremendously thick atmosphere. Such a dense blanket of gas could create immense pressure at the surface, potentially allowing for liquid water to exist even at extremely high temperatures, much like a pressure cooker. Life as we know it could not survive on that infernal surface, but it might find a refuge high above. In the cooler, upper layers of the atmosphere, floating microbial life could persist, drifting among the clouds where temperatures and pressures are far more moderate. Alternatively, if the surface is truly sterilized by heat, life might have retreated entirely into the subsurface, thriving in deep, shielded aquifers warmed by the planet's own internal geology, completely isolated from the hostile conditions above. Is Wolf 1061c a cautionary tale of a world that strayed too close to its sun, or is it a testament to life's tenacity, finding a way in the clouds or deep within the rock? The line between discovery and illusion can be incredibly thin. This is the story of GJ581g, a world that may or may not exist. Announced with great excitement, this super-Earth was initially identified orbiting a quiet red dwarf star just 20 light-years away. Its calculated position was perfect, nestled right in the heart of its star's Goldilocks zone, a place where temperatures are just right for liquid water. The data suggested a rocky world with enough mass to hold onto a substantial atmosphere, making it an instant candidate for one of the most habitable planets known. But then, other astronomers looked closer. The subtle wobble in the star's light, the very signal used to detect the planet, was called into question. Some teams argued this wobble was not caused by the gentle tug of an orbiting world, but by the star's own activity. Spots and flares on the star's surface, they said, could mimic the gravitational signature of a planet. For over a decade, the scientific debate has raged. Is GJ581g a profound discovery, or is it a ghost in the data, a tantalizing mirage created by a restless star? The controversy remains unresolved, a testament to the immense challenge of finding tiny worlds across the interstellar void. If it is real, this world would likely be tidally locked with a permanent dayside and nightside. Yet its potential atmosphere could weave a tapestry of climate, with powerful winds circulating between the hot and cold hemispheres, creating a band of temperate weather along the twilight line. Vast oceans could lap against shores in that eternal dusk, but until new instruments or methods can confirm its existence, GJ581g hangs in a strange balance, a symbol of both our ambition and the limitations we must overcome. It reminds us that every potential new home we find is a hypothesis waiting to be tested. The inner edge of a habitable zone is a precarious place for a world. HD 85512b is a super-Earth that navigates this very boundary, orbiting a calm, orange K-type star. This planet receives just a bit more stellar energy than our own Earth does from the Sun, pushing it to the warmest limits of what is considered conservatively habitable. A conservative habitable zone is the most optimistic definition, a region where a planet with an Earth-like atmosphere could potentially maintain liquid water without needing extraordinary circumstances. For HD 85512b, the difference between a temperate ocean world and a scorching Venus-like hellscape could come down to one critical factor: clouds. If this world possesses significant cloud cover, those bright, reflective blankets could bounce a substantial amount of the incoming starlight back into space. This natural planetary sunscreen would cool the surface, preventing a runaway greenhouse effect and creating a stable, comfortable climate. Imagine a world where the skies are perpetually patterned with white, shielding the land and seas below from the full intensity of its orange sun. This planet's potential for life is further bolstered by the profound stability of its star and its immense age. The system is billions of years old, offering an almost unimaginable stretch of time for the slow, patient chemistry of life to begin its work. A quiet star and an ancient orbit provide the two most crucial ingredients for complex biology: consistency and time. While we do not yet know if clouds swirl in its skies, the possibility alone makes HD 85512b a compelling target in our search. It represents a world where a simple, natural phenomenon could be the very key to its habitability. 12 light years from Earth shines a star we can see with our own eyes on a clear night. Tau Ceti is a G-type star, a near twin to our own Sun in both size and temperature. Orbiting this familiar Sun is a world of profound mystery, Tau Ceti e, a super-Earth that forces us to confront two radically different visions of a planet's fate. This world lies squarely within its star's habitable zone, but that does not guarantee a temperate climate. With a mass several times that of Earth, Tau Ceti e could possess a crushing atmosphere. One possibility is that this world is a super-Venus, a scorching hellscape where a runaway greenhouse effect has taken hold. Imagine a surface where lead flows in molten rivers under a sky thick with clouds of sulfuric acid, a permanent global furnace driven by the intense heat trapped beneath its atmospheric blanket. Yet there is another, equally plausible future for this world. It could be a vast water world, a planet with a deep, globe-spanning ocean hiding beneath a thick, steamy atmosphere. In this scenario, the entire surface is an aquatic abyss with no continents breaking the water's surface. The immense pressure at the bottom of this ocean would create exotic forms of ice, even in searing temperatures, forming a layered world of liquid and solid water unlike anything in our solar system. The profound significance of Tau Ceti e lies in its Sun. By studying a planet around a star so similar to our own, we are essentially looking at a parallel version of our solar system. We are asking one of the most fundamental questions in all of science. Is our Earth, with its balanced climate and abundant life, the rule or the exception? Is the default path for a rocky world in the habitable zone a temperate water world, or is it a scorching, sterile greenhouse? The answer, hidden within the faint light reflecting off Tau Ceti e's atmosphere, would not just tell us about one distant world. It would tell us about our own planet's place in the cosmos and whether our existence here is a common miracle or a breathtakingly rare accident. While its inner sibling presents a vision of fire or water, the outer world of this familiar star system offers a different kind of promise. Tau Ceti F is a super-Earth orbiting on the cold, distant frontier of its star's habitable zone. This position is a delicate balancing act. It receives far less warmth from its sun-like star than Earth does, and without a significant source of internal heat, its surface would likely be a global ice sheet, a frozen desert locked in a permanent deep freeze. Yet this world holds a secret that could transform its entire nature. A thick atmosphere rich in greenhouse gases like carbon dioxide or methane could act as a planetary furnace, trapping the faint starlight and preventing precious heat from escaping back into space. This is the same process that keeps our own planet warm, but here it would need to work much harder to compensate for the greater distance. Imagine a world where a dense, hazy atmosphere of orange and red tints the sunlight, creating a perpetual, dim twilight. Under that insulating blanket, temperatures could rise above the freezing point of water, allowing for vast, cold oceans to pool across the surface. This world would not be a tropical paradise, but a place of stark beauty, perhaps resembling a warmer, wetter version of early Mars. Its shorelines could be rugged and icy, with glaciers calving into dark, choppy seas. The very conditions that make it a challenge could also be its saving grace. That same thick atmosphere would provide immense pressure at the surface, which can paradoxically keep water liquid even at temperatures where it would normally be ice. Could this distant, cold world be huddled under a protective atmospheric coat, nurturing a quiet, resilient form of life in its sluggish, sun-starved seas? Data can hide wonders in plain sight. Buried within the old observations from the Kepler Space Telescope, a second look revealed a world that had been missed, a planet that now stands as one of our most significant finds. Kepler 1649c is an Earth-sized world in almost every sense that matters. Its radius is nearly identical to our own planet's, and it orbits securely within the habitable zone of its quiet red dwarf star. The most compelling number, however, is 75%. This distant world receives 3/4 of the stellar energy that Earth gets from the Sun. This places it in a remarkably temperate position, a sweet spot where the climate could be strikingly similar to our own, without the need for exotic atmospheric conditions to compensate. This combination of Earth-like size and Earth-like stellar heating is incredibly rare in our catalogue of exoplanets. Many worlds are the right size but orbit too close to their stars, baking under intense heat. Others are in the habitable zone but are bloated super-Earths with gravity and atmospheres utterly unlike our own. Kepler 1649c avoids both of these pitfalls, making it one of the most Earth-like worlds we have ever identified. Its discovery through a painstaking reanalysis of old data serves as a powerful reminder that our first look is never our last, and that the most promising answers may still be hiding within the information we have already gathered. What secrets might this planetary twin hold under its crimson sky? Our nearest stellar neighbor still has secrets to reveal. Beyond the potentially habitable Proxima Centauri b lies a second world, a distant and frigid sibling named Proxima Centauri c. This candidate planet orbits far outside the habitable zone, in a region of deep and permanent cold where sunlight is too weak to melt ice. A year on this world would last over 5 Earth years, a long, slow journey around its faint red sun. The nature of this distant orb is a puzzle. It could be a massive super-Earth, a rocky world many times heavier than our own, or it might be a mini Neptune, a small gas giant with no solid surface to speak of. In either case, the surface would be an airless, frozen wasteland, a landscape locked in an ice age from which it never awakens. Yet even here, in this profound chill, life might find a way, not on the surface but deep within. If Proxima Centauri c is a rocky super-Earth with a hot, active core, its internal furnace could be its saving grace. The decay of radioactive elements in its mantle, the same process that heats Earth's interior, could maintain vast reservoirs of liquid water trapped far beneath the frozen crust. Imagine a dark, global ocean completely sealed from the surface, warmed by the planet's own beating heart. Alternatively, the relentless gravitational tug from its parent star could squeeze and flex the planet's interior, a process known as tidal heating. This constant friction generates warmth, enough to melt ice and sustain subsurface seas for billions of years. We see this phenomenon at work in our own solar system, on moons like Europa and Enceladus, which are frozen on the outside but harbor global oceans within. The existence of a world like Proxima Centauri c forces us to expand our definition of home. A habitable environment may not require a sunny spot near a star. It could be a dark, warm sea hidden beneath miles of ice, thriving in absolute isolation. The most common life in the universe might not live under a friendly sun, but in the lightless interior oceans of frozen worlds scattered throughout the cosmos. A mere 12 light-years from Earth, a world of profound promise orbits in the cosmic silence. Lytton's star B is a super-Earth, a rocky giant about 3 times the mass of our own planet, and it resides perfectly within its dim red sun's habitable zone. This world scores higher on the Earth Similarity Index than almost any other known exoplanet, a scientific measure that compares its size, density, and received starlight directly to our home. It is not just in the right place, it has the right properties to be a true analog to Earth. What truly sets this world apart, however, is the profound stability of its existence. Its orbit is almost perfectly circular, a gentle, consistent path around its parent star. This orbital tranquility means the planet experiences no wild, extreme swings in temperature throughout its long year. Its climate, should it have one, would be remarkably steady, a far cry from the elliptical orbits that plunge other worlds between fiery summers and ice age winters. The star itself is a quiet red dwarf, offering a calm and consistent flow of energy, free from the violent flares that threaten to sterilize other promising candidates. With its Earth-like conditions, stable orbit, and peaceful star, Lytton Star B stands as one of our very best targets in the entire search. We are not just looking at a dot of light in a habitable zone. We are looking at a world that has maintained the potential for life consistently and reliably for billions of years. What kind of life could have evolved in such a stable and enduring environment? The TRAPPIST-1 system holds more than a single aquatic secret. While its sibling planet E might be a global ocean bathed in twilight, the next world out, TRAPPIST-1F, presents a colder, more enigmatic possibility. Orbiting further from its faint star, this planet resides on the chilly outer fringe of the habitable zone. The sunlight reaching its surface is weak and feeble, suggesting a world likely encased in a global shell of ice, a permanent snowball state. But in this compact family of worlds, proximity creates its own unique form of energy. TRAPPIST-1F is not alone. It is constantly tugged and squeezed by the gravitational pull of its immediate planetary neighbors. This relentless pushing and pulling creates intense friction deep within the planet's core, a process known as tidal heating. Imagine the interior of this world being kneaded like dough, generating warmth from the inside out. This internal furnace could be powerful enough to melt the base of the thick ice crust, creating a vast, dark ocean trapped between the frozen surface above and the rocky seafloor below. We see a similar phenomenon in our own solar system on Jupiter's moon Europa, a frozen world with a hidden ocean that may hold more liquid water than all of Earth's seas combined. TRAPPIST-1F could be a scaled-up version of this, a super Europa orbiting another star. Life on such a world would never see its sun or feel its warmth. It would thrive in absolute darkness, sustained not by photosynthesis, but by chemical energy seeping from hydrothermal vents on the ocean floor. Could the most common life in the galaxy be found not on Earth like planets, but in the lightless interior oceans of frozen worlds forever hidden beneath the ice? Further out in the same remarkable system, TRAPPIST-1G presents a vision of a world sculpted by ice. This planet is only slightly larger than its sibling E, but its greater distance from the faint star means it receives a similar amount of stellar energy as Mars does from our Sun. On the surface, this would likely be a profoundly cold environment, a landscape where any water exists as a permanent global ice sheet. Yet the true potential of this world, like its neighbor, lies beneath the frozen crust. The constant gravitational dance between the 7 tightly packed planets generates intense tidal heating within TRAPPIST-1G. This internal warmth, born from friction, could be strong enough to melt the base of the ice, creating a vast, dark ocean sandwiched between the frozen surface and the rocky core. This hidden sea would be completely isolated from the dim red sun above, a world entirely unto itself. In such an abyss, the chemistry for life would not rely on sunlight but on the raw materials leaching from the seafloor. Hydrothermal vents, like those found in Earth's deepest oceans, could spew mineral-rich plumes into the water, providing the energy and nutrients for entire ecosystems to flourish in perpetual darkness. The atmosphere of such a world would be thin and cold, but it could still play a crucial role. Traces of gases from the ocean below, like methane or hydrogen, might seep through cracks in the ice and be detectable by our telescopes. Finding these chemical signatures would be like hearing a faint whisper from a hidden ocean, a clue that life might be stirring in the deep. Could TRAPPIST-1G be a frozen shell guarding a secret, thriving world within? Kepler 22b reminds us that every great search begins with a first, thrilling discovery. This was the first planet ever found by the Kepler telescope orbiting comfortably within the habitable zone of a sun-like star. For a moment, it captured our collective imagination as a potential new Earth. The star it circles is remarkably similar to our own Sun, a G-type star, but the planet itself is something entirely different. It is a giant, over twice the radius of our home world. This size places it squarely in a mysterious category, the puzzling gap between a super-Earth and a mini-Neptune. So what kind of world is it? The answer remains one of astronomy's most persistent puzzles. If it is a super-Earth, it could be a massive, rocky planet with a solid surface. Its stronger gravity would allow it to hold onto a tremendously thick atmosphere, potentially creating a global ocean that covers the entire surface. Imagine a planet with no continents, just endless, deep water under a hazy, warm sky. But the other possibility is just as likely. Kepler 22b could be a mini-Neptune, a world with a relatively small rocky core utterly smothered by a deep, crushing envelope of hydrogen and helium gas. In that scenario, there is no surface ocean, no shoreline. Descending into its atmosphere, you would find only increasing pressure and heat, the gases turning into a hot, dense fluid until the very idea of solid ground vanishes. This fundamental ambiguity is why Kepler 22b remains a high-priority target for the next generation of telescopes. We must look past its size and into its atmosphere, searching for the chemical clues that will finally tell us if this pioneering discovery is a vast water world or a gaseous phantom. Some planets hide their secrets behind a veil of clouds, but GJ1214b presents a different kind of mystery, a world with a perfectly blank face. This super-Earth, orbiting a red dwarf star 40 light-years away, is one of the most intensely studied exoplanets we have found. When it passes in front of its star, our telescopes watch for the subtle fingerprints of chemicals in its atmosphere, the telltale signs that reveal a world's nature. Yet with GJ1214b, we see almost nothing. The starlight filters through a featureless, hazy shroud, a uniform blanket that gives no clues about the world below. This profound blankness is itself a powerful piece of evidence. It points to an atmosphere thick with high-altitude clouds or smog, or perhaps an atmosphere so incredibly dense and heavy with water vapor that it absorbs all the light trying to pass through it. The planet orbits so close to its star that its surface temperature is likely scorching, far too hot for life as we know it to exist on any solid surface. But what if there is no surface, at least not one we would recognize? This is where the mystery deepens into wonder. GJ1214b could be a true water world, but not one with familiar oceans. Its entire globe might be enveloped in a deep, global ocean, not of liquid water, but of a supercritical fluid. At the immense pressures and temperatures likely found on this planet, the distinction between liquid and gas blurs into a single, exotic state of matter. Imagine a steamy, thick, and soupy atmosphere that gradually gets denser and hotter as you descend, never offering a clear boundary between sky and sea. You would simply sink into an increasingly hot and pressurized fluid until you reached a layer of exotic ices, forms of water so compressed by the planetary pressures that they become solid even at searing temperatures. Could life exist in such a bizarre environment? It is a tremendous long shot, but if it does, it would be nothing like life on Earth. It would have to be a biology that thrives in a perpetual hot soup under crushing pressures, perhaps floating in the dense, warm layers of that global fluid ocean. GJ1214b may not be a candidate for a green, living paradise, but it forces us to expand our imagination of what a living world can be, pushing the very definition of an ocean to its abyss. Chinese letter. The search for life demands we look into the abyss as well as the light. KELT9b is a world of pure fury, the hottest exoplanet we have ever discovered. It orbits so close to its blue, searingly hot host star that a single year lasts less than 2 Earth days. The stellar radiation bombarding this planet is so intense that its dayside temperature soars to over 4,300 degrees Celsius, hotter than the surface of some stars. On this world, the very concept of rock and metal breaks down. Elements like iron and titanium are vaporized by the extreme heat, existing not as solids or liquids, but as gaseous atoms swirling in a scorching atmosphere. The planet is literally evaporating, leaving a tail of incandescent gas like a cosmic comet. This is the antithesis of a habitable world, a graphic illustration of what happens when a planet ventures too close to its sun's fire. KELT-9b exists in a region so hostile that the fundamental building blocks of chemistry are torn apart. Its brutal existence throws the delicate balance of our own planet into stark relief. The habitable zone is not a generous, wide pasture. It is an incredibly narrow ribbon, a fragile orbital path where temperatures are just right for liquid water to persist. A little closer to the star, and you get the molten hellscape of KELT-9b. A little further out, and you enter the permanent deep freeze of a snowball world. Our Earth and the other promising candidates we have explored exist in this precarious sweet spot, a cosmic tightrope between fire and ice. The violence of KELT-9b is a reminder that the conditions for life are not a given. They are a rare and precious alignment, a fleeting gift of orbital mechanics that we are only just beginning to appreciate. A planet where the sky rains molten iron offers a vision of cosmic violence. WASP-76b is a gas giant locked in a close, scorching embrace with its star. This world is tidally locked, meaning one hemisphere forever faces the stellar inferno, while the other is cast into an endless frozen night. The temperature difference is apocalyptic. The dayside is so searingly hot that it vaporizes metals like iron, turning them into a gaseous mist that swirls in the atmosphere. Then, powerful global winds carry this vaporized iron across the planet's face toward the cold, dark night side. There, the iron condenses and falls from the sky as a rain of glowing, liquid metal. This is a world of impossible extremes, a place where the very conditions for life seem not just absent, but laughable. Yet within this furnace, a new and fascinating idea has taken root, the concept of the Terminator line. This is the narrow, razor-sharp boundary that eternally separates the blazing day from the frigid night. On a world like WASP-76b, this line is a region of permanent sunset, a twilight band that circles the entire globe. Here, the climate could be unlike anywhere else on the planet. The atmosphere, flowing from the hot side to the cold, might cool just enough in this zone to allow for temperatures that are, for a brief moment, moderate. Could such a place ever be habitable? For a gas giant like this, almost certainly not, as there is no solid surface to stand on. But this concept of Terminator habitability is not confined to gas giants. Imagine a rocky, tidally locked super-Earth in its star's habitable zone. Its dayside would be a scorching desert, its nightside a frozen glacier. Yet right along that Terminator line, conditions might be just right. A band of perpetual twilight could host liquid water, stable temperatures, and an environment where the chemistry of life could begin. Life would be trapped in this narrow strip, never able to venture into the deadly heat or the absolute cold, but it could thrive in that eternal dusk. The violent spectacle of a world like WASP-76b forces us to think creatively. It shows us that habitability might not be a global condition, but a local one, a thin, precarious ribbon of possibility stitched between two worlds of extremes. The final frontier in our search for life may not look like Earth at all. A new class of hypothetical worlds called Hycean planets shatters our traditional image of a habitable world. These are not rocky planets with nitrogen and oxygen skies. Instead, they are hot, water-covered worlds enveloped in a thick, dense atmosphere of hydrogen. Imagine a planet with no land in sight, just a globe-spanning ocean that churns under a deep, opaque atmosphere. The surface temperatures could be close to the boiling point of water, creating a perpetual steamy haze. For complex life like us, these would be utterly hostile environments. Yet, for microbial life, they could be perfect incubators. The hydrogen-rich atmosphere creates immense pressure at the ocean's surface, a pressure so great that it could keep the water liquid even at temperatures that would normally turn it to steam. This very pressure could act as a protective lid, sealing in the ocean and creating a stable, if hot, aquatic world. The real promise of Haitian worlds lies in their sheer potential numbers. In our galaxy, planets with hydrogen atmospheres are far more common than rocky worlds with Earth-like air. Red dwarf stars, the most abundant stars in the Milky Way, are particularly likely to host these kinds of planets. If life can indeed begin and persist in the warm, dark oceans of a Haitian world, then the number of potential abodes for biology in our galaxy could be vastly larger than we ever dreamed. We are no longer just searching for a second Earth. We are searching for an entirely new blueprint for life, one that thrives not in a familiar garden, but in a pressurized, aquatic universe all its own. This journey across 30 worlds reveals a cosmos teeming with possibility. We have stood on the brink of tidally locked eyeball planets and gazed into the hidden oceans of frozen super-Earths. We have contemplated the serene stability of worlds like Lytton Star B and wrestled with the ambiguous nature of water-shrouded giants like K218b. From the familiar day-night cycles of HD 40307G to the crushing, steamy atmospheres of Haitian worlds, the galaxy offers not one but countless blueprints for what a living planet could be. This staggering diversity tells us one thing with absolute clarity. The ingredients for life are not rare. They are scattered everywhere, woven into the very fabric of star formation. The building blocks are common, but the recipes are infinitely varied. Our own Earth is just one single example in a vast cosmic library of potential habitats. The question is no longer if other worlds can support life, but what forms that life might take in environments so alien to our own. The next chapter of this great search is already beginning. The James Webb Space Telescope is now peering into the atmospheres of these distant points of light, searching for the chemical signatures of biological activity. Future observatories like the Habitable Worlds Observatory, now in planning, will be powerful enough to directly image planets around other stars, capturing not just their atmospheric gases, but potentially even mapping their surfaces. We are on the verge of moving from speculation to confirmation. The answers are out there, waiting in the starlight, so the next time you find yourself under a clear night sky, look up. Remember that you are not just looking at pinpricks of light. You are looking at neighborhoods, you are looking at suns, and around those suns, you are looking at worlds. Some may be deserts, some may be water worlds, and some, just maybe, are looking back. Stay curious, follow the discoveries, because we are closer than ever to the day we finally know we are not alone in the universe.